So now we move to the next speaker, Antonio, and we move to I think it's Piotr or Thomas. Oh, both together, okay. I don't know who's going to start. Piotr Lipiarski and Thomas Unterweissacher.
We would like to speak about two locations in Austria and several sites we have sampled last year. And our activities were to sample to different mine wastes and then weight, crush, and milling the samples, showing, polishing, and make analysis. I will show you and you also the results of it, the whole rock geochemistry, the whole rock mineralogy, and all minerals and the element components. The first one is in Salzburg, Nückelberg. Maybe you can say some words to it.
So thank you, Piotr, for letting me jumping in to present the Nückelberg area. Nückelberg is a historic mining district in the western part of Austria, where mining took place since several hundreds of years, and it was closed down in 1833. It is a polymetallic deposit hosted by Devonian carbonates and shales. And we have quite an interesting, diverse historic mine dump up there, which is quite well accessible, and therefore was chosen to collect tetrahedrite samples. Next slide. Yeah, as you can see here on the picture, the grain size of the dump is fist size, I would say. There was no mechanized processing up there. It was all done by hand. Therefore, we have areas with enriched ores, tetrahedrite ores, copper ores, and cobalt-rich ores. And that made it possible for us to collect, I would say, an appropriate sample. Okay, yeah, the paragenesis includes galena, bornite, and several other sulfides. This is another picture from the sampling campaign last year, just to get an impression how it looked like. Yeah? In detail, here we have one of the in situ samples. Back again. The black spot on it, that's the tetrahedrite. The other stuff, the whitish stuff, is carbonate rock. It's dolomite and magnesite. Here we have a detailed picture of the whole story. On the right-hand side, it's the mineralogical composition. You can see the intergrowth between quartz, siderite, chalcopyrite, and the tetrahedrite. The chemical composition has been investigated using XRF and ICP-MS with the results below. Interesting, at the Nückelberg area is quite a high arsenic value, which most probably is connected with some arsenides that are associated within the paragenesis. And when we look at the ore in general, we have around 6% sulfides compared with 94% gangue minerals. Yeah. Next one. Your turn.
Wow. The next location is in Tyrol, Schwarz, also in west of Austria. Here's an impression of the situation. The different white sites lies in the height between 700 and above 1,000 meters, and we have sampled 3 of them. The reason to choose this site was because of the high content of tetrahedrite in the made waste, as well as for the simplicity of separating ore from waste rock. The geologic, the ordovician and silurian schists of the Greyback zone are thrust upon carbonate rocks of the calcareous Alps. The extensive mining area stretches over 6 kilometers and includes dozens of waste sites ranging in altitude from 500 to 1,000 meters above sea level. And 3 of these sites were sampled. The first one is sand deposit Sandbrocher. They are rests of sand as remains of crushing stones by gravity separation with water. Yeah? It's very easy to take a sample, of course, and also to separate them. The next one is waste mine St. Antoni. It's a very steep one. It was not so easy to take a sample there. And the third one is the waste mine waste site Sigmund. Also very, very big region with a lot of different mine waste sites which are grown together in one big one. Yeah. The fractures are as well as stratiform ore bodies or polymetallic silver mercury sulfide hosts by dolomites. And mining operations have been since the Bronze Age, especially in 15th and 16th century. There's also a picture of one of the samples with results of the X-ray pulver diffractometry and XRF and ICP-MS results of the analysis, with about 2% of chalcopyrite and tetrahedrites inside. Yeah, and XRF shows us about 15% of CO2, then less than 1% iron, and also more than 14% magnesium oxide.
Okay, thanks again, Piotr. Just a few words on the steps that have been performed during the project. So we collected the bulk material from the sites. After weighing, crushing, milling, we did some separation sieving in first instance, and we tried different approaches to separate the sulfides or to enrich the tetrahedrite in the first step. That was our approach, to produce a rich tetrahedrite concentrate, which at the end not work out very well. But here you can see that the different characteristics in one slide, how the material, the input material looks like. You have the lumpy ores from Nöckelberg, the different areas in the Nöckelberg area, and on the lower right-hand side we have the stuff, which is sandy because it was crushed, mechanized. It was mechanized processing. So two different characteristics of those input samples. Here you get an impression after the sieving about the fractions, how they look like, and the next step was to try the gravity separation based on the parameter of density, which turned out to be some kind of a dead end to separate the sulfides individually. But after the discussions during yesterday and today, I think it makes sense now to get the sulfide concentrate. So most probably we were able to revive or resuscitate this dead end to bring it back to life again. Just the pyrite content is the limiting factor. So that was one of the outcomes. And in future, there are additional processing steps planned, test work is planned, and investigations about the extents of the mine waste sites, volumetrics, and heterogeneity of the resources there. They need to be investigated to get a proper classification. If this can be used as an input, as a secondary raw material source for raw materials, in short words. Thank you.
Thanks. Now from Austria, we move to Spain. So it's Concepción Fernández Leyva, which will explain us about the tetrahedrite process in Spain.
Hello everyone, good afternoon. My name is, as you can see on the screen, Bruno told us Concepción Fernández Leyva, but you can call me Concha because it's shorter It's easier to pronounce for you. That's all. Hello. I'm going to talk about our activities carried out in the framework of Work Package 2, oriented to the recognition of the Tetrahedrite mining site in Spain. To start, I'm going to introduce the team members involved in the START project. The team leader, Esther Boixereu, is a geologist, specialized mineral deposit and mineral resource mapping. Concepción Fernández Leyva, it's me. I'm geologist as well, and work in the same topic than my colleague Esther. Ramon Jiménez is a geologist and specialized in mineralogy. Paula Adanez San Juan is a geological engineer, and she's an expert in environmental impact of mining. And finally, our colleague Jesus Reyes, who is chemistry and expert in mineralogy. Oh, sorry. My goodness. So, taking into account Spain is a country with a considerable size, about 500,000 square kilometers, with a varied and complex geology and with a strong mining tradition. A priori, the potential in tetrahedrites is high, and we will therefore be in a position to select optimal mine waste site to supply these minerals to START project. Following the methodology proposed by the working group, we can see the different working stage on the screen. Being the first one, the inventory of points with potential mine waste sites. The second one, the field data collection campaign, and the third one, the field and the laboratory characterization of samples. All of them contribute to the data interpretation. To carry out the inventory of these points with potential of mine waste sites, the first source of information consulted was our IGME's mineral resource databases. There is a list with all the occurrences and mines, both abandoned and active, through Spain. In this first search of the database, 250 sites were selected, though there were tetrahedrite was mentioned. From these 250 sites, a new selection was made, keeping those points in which tetrahedrite appear at the main mineral. So there were selected 50 sites then. Eventually, the sites of interest were reduced according to the criteria discussed below, information that we can find in the database itself or in the related bibliography. So we are taking about the percent of tetrahedrite in the mine waste sites, grain size of grain size of tetrahedrite and volume of mine waste and their accessibility. Finally, 25 sites were selected, and the main problem was the information of these points was not really verified, so it was necessary to go to the field and check certain information. Well, as you can see in the slide, this is the map of Spain. Well, sorry, in Portugal as well. In the Iberian Massif, all those on the left all those on the left and different zones, we select 11 mine waste sites. 4 are in the Cantabric zone, 2 in the Asturiano-Leonesa zone, 2 in the Osa Morena, and 3 in the zone Superturesa. On the right side, we are 2 in the Pyrenees, 6 in the Cordillera Ibérica, 1 in the Sistema Central, and 1 in the Cordillera Ibérica. In the second stage, we proceed to the field data collection campaign, being the final objective, the validation of the previous selected sites. A point that match that avoid criteria was sampled and characterized. All of the points selected a priori, and we have been definitely selected, while a large number of being finally rejected for two main reasons. The percentage of tetrahedrite was not enough, or the volume of mine waste was not really important. Well, then let's see, I don't know if it's good, the image, which zones have been definitely selected from all of the beginning we tried. From the Superportuguesa zone, only one seems to be interesting, which is the Serrecilla mine, because the mineral is abundant, although the volume of the mine waste is not too high. Regarding the Tarsis mine, although discarded at first due to the fine grain size of the mineralization, we have reconsidered it again for the high volume of mine waste, by millions of tons. So although the problem is the grand size, are trying to deal with this difficulty, and we count with the support of the mining company to try to solve this problem. So maybe it's a point to keep. In the Asturiano-Leonesa zone, the one with more possibilities is Peña Negra, but the volume mine waste is quite limited. So maybe we are trying to keep, or we are not really sure. In the Cantabrica zone, only Coriello, but with the limitation both in percentages of tetrahedrite and volume of waste dump. From the Cordillera Ibérica, Torres de Albarracín seems to be very appropriate. Apart from tetrahedrite is abundant, there are several mine ways to be sorted. So not just once, but several around it is possible to find mine waste. So maybe it's quite interesting. In the system central, the selected size has finally been described because tetrahedrite is really scarce. The rest of which appear on the screen have not been sampled yet, waiting for the outcome of the above ones. Although Cordillera Ibérica seems very good, Lanteira, it's a very good place to visit and check it, but we didn't have yet. So of the 4 sites currently considered good, 2 of them are being studied now in this moment, Torres de Albarracín and the Serrecilla mine. We are involved in the field and laboratory characterization of sample of these sites. A quality analysis of the samples for both, for Torres de Albarracín and Serrecilla, has been carried out with SIM, which has enabled us to identify the mineral and identify other sulfides too in the sample that could be confused at the time of the separation. Besides, with SIM, we have detected the alteration in the samples. The raw samples were crushed, which was determined by observation under binocular magnetization. Then the samples were homogenized and coated, and then crushed again and divided into several fractions from below 0.1 to above 1 millimeter. For sample from both sides, we have ordered polish section to achieve the mineralogical characterization. According to their mineralogical composition, we have to try to carry out mineralogical separation test. For the sample from Torres de Albarracín, the most favorable proceed for the moment, we have passed them through the Franz magnetic separator, so we have been able to discard the sulfide sediments. Then we attack them with acid to remove impurities. In Serrecilla case samples, the mineralogical separation is still in discuss because the grain size is very small, and we have many problems to decide which is the better to use. And by now is all the work carried out on the different tetrahedrite mines in Spain. Thank you for attention. It's okay?
We'll take care of that.
Okay. You want to talk?
And now we go back to Central Europe. Stanistav Šoltés will give a presentation about Tetrahedrites on the Mária Mine in Rožňava. So here we are.
So, hello everyone. My name is Stanistav Šoltés. I'm from Štátny geologický ústav Dionýza Štúra. It's a geological survey for Slovakia. And we are involved mainly in work package 2, providing the concentrates of tetrahedrites. Rožňava mine is in eastern part of Slovakia. It's here. Oh, it's not showing the pointer.
To the right. Far to the right.
Okay, so it's here eastern part of Slovakia. And Mária Mine is situated in metasedimentary metavolcanic formations of early Paleozoic Dionýza group. The Rožňava ore field area is penetrated by the subparallelly arranged multiple epigenetic hydrothermal siderite sulfidic veins of southeast-northwest direction. Mining in this ore area started in the 13th century. It was mainly for gold, silver, copper, antimony, and mercury. This new strieborna, in English silver, vein was discovered later in the year 1981. The ore sample is from 6th level of this Mária mine, which is 200 meters below the surface. This is how it looks in the mine. The major vein minerals are medium to coarse grained siderite and younger quartz sulfide mineralization. The most abundant ore minerals are tetrahedrite, chalcopyrite, pyrite, and arsenopyrite. The high content of silver in tetrahedrites was the reason for the name of the Strieborna silver mine. The raw sample, what we sampled in the mine, was crushed, homogenized, and quartered. This is a scheme, and here are the circled samples were the provided samples of concentrates. The fractions were processed by electromagnetic separation on dry way at different intensities of saturating electric current and fraction below 0.1 millimeter by flotation. Detailed procedure is in the report. It's on the SharePoint. If somebody would like to look for it, it's there in work package 2. So the flotation for the separation was also tested, but it was not effective, and also gravity separation was not effective at all. Here is how it looked like the final concentration samples. It is in different grain sizes, from 0.1 to half millimeter. And the amount of tetrahedrite in these samples varied from 82 to 97% of tetrahedrite. The inputs and products were characterized by X-ray diffraction analysis, and this yellow part is the diffraction analysis of these samples provided. There were also chalcopyrites, siderites, quartz, and other minerals. The chemical analyses by XRF were performed in accredited laboratory, and it's part of the structure also the iron with 4 to 5% in structure. The chemical composition of minerals was determined by using a wavelength dispersive spectrometry on a microprobe Kameka S600 on our Department of Electron Microanalysis on our institute in Bratislava, Slovakia, and most of the grains in concentrates were tetrahedrites, but part of them are overgrown by other minerals. So, for example, this one grain consists of tetrahedrite, but also chalcopyrite, arsenopyrite, pyrite, quartz, siderite. So it's not possible to separate it 100%. So far, we have obtained approximately 4 kilos of tetrahedrite concentrates. We are working on more concentrates. We are planning to have more sampling, more processing, more delivering of concentrates. Thank you for your attention.
Place there was resin.
You can start your questions.
Which one?
The dark place is resin, right? In the ring.
Which one? This?
Yeah, between the particles.
It's quartz or resin. Yes, resin. No. Mm-hmm. Because it's a concentrate. Thank you.
Just stay there.
Okay.
Can you put the composition again?
One from microprobe or
Yes.
no? This is bulk analysis, etc.
Yeah, it's good.
Mm-hmm.
It's good. You see the amount of copper?
Copper, yes, high amount of copper.
Should be 35. It's 36. I know.
Concentrate.
Yeah, so, but then you have 80%. You see, I think we can use more copper than.
I think when we analyzed the grains, tetrahedrites by microprobe, the amount of copper was more higher.
You don't know how much.
I have it in table.
You know it, I can see it for tomorrow.
Yes.
Can I based on the table where the values don't add up to 100 but to 70?
No, this is not adapted to 100%.
They add up to 100 values too? I think they add up to 70.
Maybe. I'm not sure.
Because I worked in central calculation.
I have to
So all
see
the
the tables.
percentages are with yeah,
Maybe I will give everything to SharePoint. And
okay.
so if more questions.
Okay, there are many questions from the audience remotely, so maybe I can read that. Okay, so go in order, and probably the first questions are for Antonio, mainly, but there are also other questions there. So Sebastian says, you mentioned metal tonnages of the Bergberg Goldfarb mine. Do you know the quantities of mine wastes, and how did you quantify the volume of the Ramlesberg mine tailings?
So the total tonnage of the whole mining waste I don't have now in mind, but so the data that I provided was quantified in a previous project. Someone researched about the mining waste. They were looking for raw, so critical materials there. So
And then, I think it's again for you, there's a question from Alessia Korami. What about the remediation of these areas? One knows what. Maybe Alessia can explain. The next question then, from Antje Wittenberg. Thanks, Antonio. You showed the size and the intergrowth of tetrahedrite, like the Austrian samples. This causes a question for Doug. Doug is not here now. Would you believe it would be suitable for forcing use, or would you rather use synthesized tetrahedrites in any case? So you don't have Doug. Is anyone able to answer the question? Probably not. So we have to move forward. Next question is again, okay, no, I think it's for Piotr and Thomas. The content of tetrahedrite in Germany and Austria is comparable to other mines in Europe.
More comment than a question.
No, it's a question. Is it comparable to?
Difficult to say. If it's comparable. What do our colleagues say? We have 6% of sulfides, including all the different minerals, including tetrahedrite. So,
Maybe similar genetic associations.
so we are well below 5% tetrahedrite in all of the minerals.
So this,
Well below.
And in total sulfides?
Sorry?
And in total sulfides?
In total sulfides, we are in the range, I would say in the range between a few percent up to 10%. But that's depending what you, when you look at the historical mines, waste site, it's different compared to an active mine. So we are talking about grade here.
We're talking about waste. Yeah.
Not one way.
Of course, yeah.
So in Germany, it's also the same. So
Yeah.
in our mining waste, we have very less.
Much less, of course.
Because tetrahedrite was also a subordinate mineral in the primary ores. So that's the problem.
Maybe this question leads me to a general comment. Because Julie was mentioning the UNFC, the UN framework classification for mineral resources. And it's quite difficult to classify historical waste sites, tailings dams, depending on what age they are. If we have a medieval waste site, it's completely different compared to a modern one. And how to put this into a modern classification system, put it into resources with the different classifications, I don't know how this should work or could work, I think. With the deposit, we have geometrical constraints. We know the deep strike of a vein, for example. So we can estimate it in a geometrical view. But with the tailings and the historical waste sites, I don't think we have this. So this is a separate question. We are not able to answer it, in my opinion.
Okay. Next question again from Antje Wittenberg. Have you used also electrical pulse minerals? I think it's for you from Austria. Have you used also electrical pulse mineral disintegration? There is or was a facility at the open to separate the tetrahedrite from other minerals as much as possible as one of the first steps of separation.
So that's the answer is quite easy. There was a facility in Rome, so we were not able to use this facility.
Next from Sebastian Fleiderer. I have the same question for Concepción as for Antonio. How did you quantify mine waste volume? So.
The data that I have provided here are from some papers or some investigation that were previously done in Germany. So it's not something that I have done myself.
The screen is from our database. Yes, this is very full of the same. We have this information more or less.
It's an historical.
Yeah, it's historical.
For that. Fernando Oliveira, something must be representative of the mining waste. How is this done to guarantee accurate data of the tetrahedrite content? Doesn't say for whom, but maybe you can comment.
I would say sampling should be representative for mine waste. It cannot be representative for a historical waste dump, simply speaking. But we can do a best effort to get a nearly representative sample. That's what is possible, nothing else.
Like working.
Taking the sample. When we look at the sampling, a volumetric body with heterogeneous composition, and we do not know the composition, we cannot take a representative sample. We can have a representative subsample of something that is nearly representing this historical mine waste.
So in our case, when we collect samples, we drill, we make different drill calls, and then we analyze from different drill calls, so the sample can be representative. Of course, the tailings are not homogeneous, but that's how we do to assure that sample are representative from the west side.
Bruno, can I get in there as well?
Sure.
Yeah, so I understand where that question is coming from and where it's going. Because for you to get a representative mine waste sample, you first of all have to lay a grid over the area, drill every single bit of that right to basement rock, and then you would have to see whether it's stratified or not. And when you find the stratification, you would collect the sample at every single different stratification. However, in start, we are not looking to collecting representative mine samples from mining waste. We are looking to supply a specific raw material for use in a specific device, in this case, a technological device. So we're not worried about that. We should be worried, but we don't have the time or the money.
No time for it.
Well, start to. Another question from Tersi Aguata for Concha. What is the criteria for rejecting waste zones bay? One example.
Yeah, for example, passes, although it's reconsidered now, the site of the Iran site is very, very small, although there are lots of tons of waste. The problem with the site of the green site is very important for us.
There's again from Sebastian Fleider, it's comment and question. It's very hard to measure average tetrahedrite content of the entire waste material. It needs representative, that means a lot of sampling. Are there perhaps geophysical methods instead? So it's again the same problem.
I don't think geophysical methods will be able to detect tetrahedrites. Unless it's in a big mess.
What a simple answer, no.
Yes.
Simple answer is no.
Tell Sebastian, no.
The volume of the waste.
You can measure the volume of the waste. That's a different question.
Okay, that was.
We spent hours on the waste to find some fiber. It was not so easy. And I think what we took ancestors from the waste, it was maybe 1 or 2% of it, and from it we had 2% of tetrahedrite. Yeah, and we have 0.0001 or so. Very little.
Yeah. Okay. I think we've gone through the list from the remote connected people.
I need to speak to Concha.
Yeah. Publicly or?
Yeah, right now.
Right now.
So, just as a comment, yesterday, Alviz and I were chatting about alternative materials. He mentioned it this morning, that whether we, instead of supplying a tetrahedrite, which has already got all the different, the copper, the antimony, blah, 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 whether we could focus on different materials that, say, a copper material, a antimony material, and some other material that will have a larger composition of the element that we're working with. Now, I saw that you presented Yen de la Encina mine, which is very close to Madrid. And I know that that was a silver mine, but they also have antimony, namely fibergite. Did you detect any fibergite when you went there?
He's talking about Valentina.
Fibergite, did you see fibergite? Yeah. I'm not saying that you should sort of go back and redo all the thinking.
Yes, it's very
But
close.
if you sort of happen to be wondering why, collect some fibergite, bring it.
That would be really great to have.
You want it?
Yeah, maybe a copper-based material.
Esther is saying there's very little.
There's very little.
Very little.
Then, yeah.
Okay.
Okay, any more questions for the speakers of today?
I just wanted, this is really curiosity, but how many of the countries have any programs to fight or to deal with acid drainage from these tailings? There's no, I'm asking because in Norway it's a big issue. There are rivers which are completely acidified, and the fishes are all killed, and they are always discussing this. And I wonder if in your countries this is ever discussed already.
We have some localities which are also this time treated, and it's lavated drainage of acid mine waters from mines. There are some reservoirs where it's sedimented.
pH is changed.
Small, it's one area.
And the other question I have is that pyrite is it used for anything? Does anybody buy pyrite for anything?
Not now.
Only the museums.
We have some art.
Yeah.
Yeah.
It's from factories, a lot of sulfur.
Yeah. So I'd like to come back to Patricia's initial question on the AMD. For example, Portugal does not have a program for actively monitoring AMD. However, we are very fortunate that where we do have AMD, that it's in a closed basin. So the water gets in, okay, it turns red, but it doesn't go anywhere, it stays there. Now, Rio Tinto would not be anything special if it didn't have AMD. I don't know if you know Rio Tinto.
I don't know by name.
Yeah, that is a fantastic place, you must go there. And it doesn't kill all the fish, don't worry, no.
Okay.
It doesn't kill all the plants either.
Okay.
Because there's a thing called, what's the name of that plant that likes acid mine drainage? Erica and Valensis, from the Andevolo area. Erica and Valensis.
They like citric acid.
Yeah, they do. They grow beautifully on the margins of these red rivers. You don't know Erica and Valensis?
I don't know.
No. You don't think about the little purple flowers? You've seen it for sure. It's from Andevolo. It's endemic to Andevolo. Yeah.
Guys, we're live in work.
Sorry, it's my botanical side coming through.
There is a comment from Sebastian Pedra for Daniel. Yes. No fibergite in the Austrian samples found so far.
Okay, excellent. Thank you, Sebastian.
Anything else? Any more questions, comments? I don't see anything else from the unfortunately, Alessa did not explain better questions, so we cannot answer that. Nothing else, then we should thank the speakers again. Including the two speakers that we had before, of course, from our scientific advisory board. And this is the end of the seminar, the webinar, sorry. And thanks for being here, everyone here in Madrid. We're about 30 people here for our meeting, and about 30 that we had also online. So thank you again, and enjoy the rest of the day.